Hello guys, welcome to another video of instrument control using Labview. So in today's video I will try to show you how to make Labview program for measurement of Seebeck coefficient. Uh, if you are working in experimental condensed matter physics, then you must know about what is Seebeck coefficient. You can see little bit Seebeck coefficient. It is very important transport measurement. It gives information about many things. Here is the formula for Seebeck coefficient. What we have to take? We have to take voltage gradient and temperature gradient. In order to calculate Seebeck coefficient of any material, we just have to divide its voltage gradient by its temperature gradient. So let's see how. What you need to have for Seebeck coefficient measurement is, first thing, obviously you should have some sample. Sample have some finite dimension. Like suppose 1 into 2 mm square will be good. Okay. You should have some of finite dimension. Second thing, you should have some DML. You should have temperature controller. You should also have a thin film heater. Creating delta T, and you should have differential thermocouple to measure delta T. Okay, so these things will be required in order to make measurement for Seebeck coefficient of any material, of any sample. Let's see what is the process of measurement. So what we do, suppose we have a sample of finite dimension. This is our sample. We attach a thin film heater at one end of sample. Say this is a thin film heater. You might have heard about this thin film heater. You provide current and it start heating the sample. It create some temperature gradient. Okay, this is thin film heater. You are providing current to this heater and this is creating temperature gradient. You will measure, you will put two voltage lead here the help of these two leads, you are going to measure delta V, okay. With the help of these leads, you are going to measure delta V, and you will put a differential thermocouple for measure delta T. This is differential thermocouple. You might have heard about this also, differential thermocouple. These two wires are of copper and this may be of chromium. This may be of constant. This makes a differential thermocouple. You can measure delta T with the help of this differential thermocouple. Okay, and you put this entire setup within temperature controller. And you can attach this box with temperature controller, and you can vary temperature of this box, and at different temperature you can have graph between Seebeck coefficient, yes, and temperature. This is important. This graph is important. You can have any shape, and with the help of this graph you can explain property of material. Negative value of Seebeck coefficient tells the dominance of electrons, and positive value shows the dominance of holes. So you can see related physics of Seebeck coefficient. But anyway, what we just trying to make setup or make arrangement to measure Seebeck coefficient of any material. You can see some already measured value, like if we see in images, then there are many materials whose Seebeck coefficient has been measured. This one is good, I think. You can see this one. This is example. They have measured Seebeck coefficient of lead, silver, copper, and all the metals, tungsten also. So you may see this is graph between Seebeck coefficient and temperature. So this kind of measurement, if you are looking for, then I will show you the way how to make arrangement for measurement of Seebeck coefficient. Okay, so okay, let us try to make program for this Seebeck coefficient measurement. So you know, I want numeric control. First I want to make a proper, you know, temperature controller. So this is going to be start temperature. You know, temperature cannot be too high, so we will fix it. We will put data entry to, you know, between 0 to 300 Kelvin, say, or 500 Kelvin will be good. Again we will make end temperature. We will also fix range for this end temperature. This is also going to be between 0 and 500 Kelvin. Now again we want scan points. On how much point we want to scan temperature. We also want we also want some kind of a stabilized time. Will be in second. Scan points will be, you know, can only be integers, so we will set it for integers, and we want some indicators, numeric indicators. This one for current temperature, and again error in temperature. So this is kind of, you know, user interface. it is good practice to decorate your interface. So this is temperature controller. And again, while measuring Seebeck coefficient, we will get value of we will measure value of voltage difference, delta V, and we will also get reading of temperature, gradient, delta T. Then we will have reading for Seebeck coefficients. Seebeck coefficient, yes, and we will also put Boolean indicator this will show you temperature gradient is high. This will make a signal. We will change its color. It's off, on, off, on. Okay. I will also decorate it. I also want a graph. XY graph will be good. Between temperature and Seebeck coefficient.
That sounds good.
Okay, so this is my front panel for Seebeck coefficient measurement. I can decorate it little bit more. It is up to you, but I like to make everything in very decorated manner. I always want to give my perfect shot for these things. This is my hobby, you can say. Little bit bigger I want. You can also change its color. You can select any color you like. I think this one is perfect. Now let's come to block diagram and see how to arrange these things. So first of all, I will make one second, please wait. So to palette. Okay, yes. First I will make all of them as small. This one. Now I will create things for temperature control. So for this I will take start temperature and end temperature, and on numeric let subtract in temperature will always be higher than the start temperature, so we will put it at first place and second. Now take divide, and it will be divided by number of scan points. Now I just will take for loop here. I will connect this for loop with number of scan points, and this is divided temperature and this is start temperature. Again I will take multiply. I will multiply this divided temperature with number of iterations, and then add it with start temperature. So this is temperature selection. We can check it by making indicator here. Let's come on block diagram. This is integrator. We have put for settings. Suppose we have selected the start temperature as 100 and end temperature as 200 and 10 scan points. So it means we have to start from 100 to and go to 200, and there should be 10 stay points. Okay, so this I will run this program. So in reverse order. See this is changing from 140, 50. You may run it again like it's 100, 110, 120. So it will go on. Okay, it's good, it's working. So that's all we wanted. Okay, now what I want, now I will create case structure here. I will use Labview 331 model temperature controller. So I have to initialize it first. Then I have to set temperature. So I will select configure set point here and connect it with initialize VI and then give command of temperature. Okay, so this will set some desired temperature, and again, I need to see what is temperature, so I need a sensor, this one, and I will connect with it's okay now. Here we can get reading, Celsius reading and Kelvin reading. So I would like to use Celsius reading, so I will make it indicator. Not this one. It's current temperature. Okay, it's okay now. What okay, what is generally, we give command, and we do not get exact temperature at the same time. It will take some time to reach that temperature, and although there is some error, although there is some finite error at all the time, so what we do, okay, so what we will do, we will measure error in temperature. So for this, I will create difference between current temperature and set temperature value, and that shows error in temperature. That shows error in temperature. Okay, we do not want much error, so what we do, we just make a while loop and put everything inside this while loop. Okay, make this one a little bit bigger, and this one also. Now in comparison vi, this is less than, and this may be constant, so one, and this one too here. Okay, so whenever error in temperature is less than 1, this loop will stop working, and this will go ahead, and if it is not, then it has to repeat the same process again and again and wait for some time. So we will just create waiting process kind of. So this is good, I think. We'll connect here and connect here, and we will wait for some time. I will put 1000 millisecond. So whenever this temperature is greater than 1 Kelvin or 1 degree centigrade, this will wait for 1000 and we'll check it again. Okay, so in this process we minimize error in temperature between set and actual temperature, and it should always be less than 1 Kelvin, or you can fix according to sensitivity of your instrument or sensitivity of your measurement what you need. And this section is for temperature setting. Okay, and again I will also add a frame after this, add frame after, and in this frame I will also put a weight multiply. This will convert millisecond into second, and then I will put stabilized time here in this loop. So it will wait for temperature stabilization. You can give any second for this stabilization. Now in this is wait for stabilization. In third frame you put all the measurement you want to perform. So this is measurements, all your desired measurements will be done here. We also want to check what is current temperature at the time of measurement, so I will paste the same guy here. This is measurement temperature. This is temperature. At the time of measurement. Okay. So it will go outside. Now we have to close this temperature controller, so I will put close VI here. Okay, so we have put all the things for temperature setting, for temperature controller. Now we will try to make measurement with digital multimeter for Seebeck coefficients. Okay, now in order to measure temperature gradient and voltage gradient, I will use Keithley DMM 6500 digital multimeter. Okay, so it is good to use its instrument driver, some of its instrument driver, to make the measurements. So I will go in instrument drivers in it's this one. Okay, so first I will initialize it. multimeter I'm using. I have also a 10 channel scanner card. Okay, as you know that in Seebeck coefficients you have to make two main measurement. That's the first one is voltage difference and second one is temperature difference. So you should have two different sources for two different instrument for either you should have two different instrument to measure these things, or you should have a 10 channel scanner card kind of things that you do not have to change these things during measurement. Okay, so uh, I will use that one. So it's okay. So I will come straight up to here, not this way, and again straight up to here. It's okay now. Now I will open measurement VI. This one. So first measurement I would like to have for voltage. So and this will be in channel 1. So I will put 1 here, and the function will be DC voltage. Okay, and its reading will appear here. It's voltage gradient. And then I will again put this measurement, and this time measurement will be performed from channel 2. Okay, not the same channel. in this channel I want to measure temperature gradient. So see, in differential thermocouple you cannot measure temperature difference, you just measure voltage difference and then convert it according to data sheet of type of thermocouple used in temperature gradient. Okay, so this will also be DC voltage. Okay, you may convert it later in temperature, and I will also make a single point measurement here. And we can have reading for temperature gradient. Okay, and this temperature gradient should not be very high, so what we can do, we can make a case structure while loop here. And we can again put a comparison VI here, and this should be constant. You can fill value according to your use. Suppose in this case I have select it should be less than for 5 millivolt, so it should be 0.005. okay, if it is less than this much, then this loop will be end, and also it again I will select greater one here, not with this one. So if this is greater than 0.5, then it will send signal on front panel to just reduce the current in thin film heater. Okay, to maintain a minimum temperature gradient, it is required, so it should send signals. It will now very basic things, and anyone should know. And again, we can make something for wait for some time. To reduce temperature in thin film heater. Here I will wait for 1 second, say for 2 seconds. Okay, so this thing has happened. These things are okay for multimeter. And again we will close this one also. Close VI. Where is this close? Oh my god. It should be for lost value. Okay, so now the programming part is complete. Now we have to save data. Okay, but see, one important thing we have forgot, that actually whenever you will put probe for voltage measurement across the two ends of sample, there will always be some voltage that is called offset voltage. So in order to calculate Seebeck coefficient, we should reduce this offset voltage. So first we will measure the voltage difference across the sample before we start measurement. So we will first put measurement VI here. Sorry, this one, and also we will see data, what is value of offset voltage. Okay, so we'll connect this one. This measurement should be for channel 1, and function should be DC voltage. It's okay now. And this is, you know, offset voltage. You must have heard about this offset voltage. So we have to reduce every time this offset voltage. Okay, now we want to plot this graph and save data. So what we do, we just add another frame. we will just add another frame. And in this frame, I will put this one. This is value of delta t, and I will reduce offset voltage from here. So this is actual delta V. This is not actual delta V. Delta V offset compensated. And here we will get delta T. This is delta T. Now we will divide delta V with this delta T, and multiply it by -1. And this is Seebeck coefficient. Yes. This is Seebeck coefficient. Okay, so we have calculated Seebeck coefficients, and now our next aim is to plot graph between Seebeck coefficient and temperature. So for this I will just build an array. I will here and replace it with shift resistor. And bring it here. Connect this Seebeck coefficient. To here. Okay. And the same things I will do for temperature. Also I will replace it with shift resistor. Then with this one. Okay. And I can add another frame. So the upper one is for Seebeck coefficient, and lower one is for temperature. I can create bundle. This graph here. Okay, so this will plot graph. Now I also want to save data, so I just write file IO, write elementary spreadsheet, and also build array. To the data, so 2D data and make it control to put file path, and I have to make it transport. Okay, so it's complete now. What we have done, we have first make program for temperature controller, then we have used Keithley DMM 6500 for voltage and temperature gradient measurement. We have also compensated its offset voltage, and we have tried to plot graph between Seebeck coefficient and temperature, and also try to save data. Let's see what happens on the front panel. Some arrangements we have to make on front panel, like some settings we have to do. These things will be adjusted here. You stay here. Yeah, little bit above, and also you use. Should be somewhat smaller. This me here. This is good. No problem. Okay, and this is delta V offset compensated. It should be here. This is also important. It's okay now. And this is offset voltage. Measure temperature. measurement temperature. And this is error in temperature. This is also important. We have to also adjust offset voltage, so that should be here. Okay, and we'll again put it here. So okay, it's complete now, and we will lock it, because it should not be move. It should not move in a random way. This should be somewhat little bit okay, this looks nice, and you may do somewhat more according to your use, according to your convenience. So this is program for Seebeck coefficient measurement, and to plot S versus T, and also to save data. Look, when you use actually this program for your setup, then there may be some kind of error, because for proper operation you should have instrument with you. But I have made this program with my experience. So this may be this will give you some idea how to make program, and you can make similar program for your instrument and for your purpose. So thank you for watching.